first row here. I start with the commercial splitter 1 to 4. The theoretical attenuation should be 6 dB. The real attenuation is 7, which means that just inserting the component, I lose an additional dB. This should be 9, is 10.3. In this case, the insertion loss is 1.3. This should be 12. I have 13.4, which means the insertion loss is 1.4. The general trend is that as soon as I increase the number of outputs, let's say the splitting ratio, the insertion loss will increase because it is more difficult to build a component, and you make some errors during the construction and you increase additional losses. A very important parameter, we had the occasion a few slides ago to speak about it, is the return loss. You see that for this kind of component, the return loss is higher than 55 dB. It means that if you have a signal which is entering the device, the reflection will have an amplitude, a power, which is at, as a minimum, 55 dBs below. So it's a common parameter also for electrical system, but it is the first time we got it in this presentation, so that I have insisted on it. Device or branching components, as you like to call it. Well, it is very important during the design phase to have an idea of the final evolution of the network, because the network is to be dimensioned for the final capacity, for the final required capacity. Since when the network will reach its maximum capacity, an upgrade will be possible only inserting new components or replacing the old components, but you must be sure that you have enough margin to be compliant with the new component. For example, if you want double the number of customers, you will need another 3 dB. If you have them because you are operating the network with a very good margin, you will succeed. Otherwise, you have to replace the part of the optical plant. Moreover, since branching components are placed outside, they should be compliant with the recommendation on environmental aspects. How to design an optical distribution network? Well, the maximum allowable loss between the points S and R are given in the relevant recommendation. So I know that for a specific plant, I have, for example, 10 dB or 20 dB or 30 to be spent. This optical loss budget includes everything in the plant, which means fiber, splices, splitters. It has the same value for the two direction even if it is not really very true, because you can have different losses in the two directions due, for example, to the fact that the splitter can have different insertion losses in the two directions. The system performance will be influenced by not only by the loss of the fiber plant, but also by the difference in losses between the minimum and maximum attenuation. Other parameters to be considered are the output power of the optical line transmitter or of the ONU, and the sensitivity of the receiver and the dynamic range of the receiver, which means at the end overload. You cannot exceed a given power level, otherwise your receiver will stop working. Well, let me see how many slides are left. Most important parameter is the attenuation, but also the difference between the maximum and minimum attenuation is of importance. Regarding the parameters, it must be said that they have to be acquired as the worst case values over the entire bandwidth in which the system will operate, and over the entire environmental conditions, which mean the temperature range that we might expect to have during the operation, and also other environmental aspects. All the definitions of the parameters of the optical distribution network are exactly the same that are defined in recommendation G957, which is an historical recommendation, the first one to be approved concerning optical fiber transmission system, and which deals with transmission system for the digital hierarchy on a single channel interface. As we saw yesterday, the optical distribution network contains some splitters that are distributed over one or more levels. And we also said that the most common configuration are those in which just one or two splitting levels are adopted. As we can see as we will see in the following slides, in a three-branched optical distribution network, several optical paths can be identified, and they, in general, will differ among them. They will not be equal optical paths, which means they will have different transmission characteristics, starting, for example, from the attenuation, which will be different for each branch. This is a typical configuration. As you can see, we have an optical line transmitter
an optical network unit, and in the optical plant we have several splitters which are distributed on several splitting levels. What can be said? That we can enumerate a number of different optical paths. This is one optical path. This is another. This is another one. This is another one. Of course, since the leaves of this tree will be 32 or 64, in an optical distribution network we can have 32 or 64 of different optical paths. For each of them, we have to set a table in which all the relevant parameters are listed. Now, we enter into details for gigabit-capable passive optical networks. Why we consider only this one? Because there is substantially no difference between broadband passive optical networks, the G-PON, and the gigabit passive optical network, save the data rate, which is much higher in the gigabit PON, which 4 times higher at least, and the protocols by which the data are transmitted, which means we have typically ATM in GPON and general framing procedure in G-PON. But since we are considering only the physical level, we are not dealing with protocols which are not really tied to the optical layer of the network, we will insist only on G-PON. This is a typical representation of the network. As you can see, we have, starting from the very left, we have the access node in the central office, and the passive optical networks is on the right of this central node and is connected to the central node through the OLT. The exchange is able to divide the services coming into the network and arriving from the network into narrowband services and broadband services, which means we can have here E1, which means 2.048 megabit per second, which means telephony, or this is the American standard. And on the broadband side, we can have gigabit Ethernet or some level of SDH. I will repeat some important points that were already dealt with yesterday, because they must remain in your head since they are very important. In the downstream direction, which means the direction from OLT towards the optical network terminators or optical network unit, is a high bit rate stream with TDM, time division multiplexing. No guard intervals, the transmission is very regular, so no bandwidth is wasted. The transmission is of a broadcast type, which means that all information reaches all destinations. It is up to the protocols to separate the information, and each ONT will retain only the information that is provided to it. Since it's a broadcast system and there could be some malevolous intentions, all data are crypted so that only the legitimate user can decode it. When the data reach the user, they can be sent to the home network and they can be separated into telephony, data, and video, which means triple play. On the same network, we are running 3 different kinds of services. On the other side, starting from the very right, the access to the network is on a TDMA basis, which means time division multiplexing access, and the sending of data is in burst mode, which means that each ONT will not send a continuous flow of information, but will send information only when information is available and only when it is allowed to send information from OLT via a suitable protocol. The other important thing we saw yesterday is that since the various network terminations are at different distances from the optical line terminal, some ranging procedure is to be foreseen in order to have the distribution to any of the ONT of the timing information, which means the phase according to which they must transmit their packets. And moreover, since the difference in the path length can be as high as 20 kilometers, also the power which is sent into the network by each ONT should be reduced or increased according to the distance. So the most distant ONT will send the maximum power. The OLT, which are the nearest, which are the nearest to the central office, will send the lowest power. So that when the packets reach the OLT, they are in a narrow range of amplitudes. The physical reach for the completely passive optical network is, as we said yesterday, 20 kilometers, but with reach standard that we will deal with later, the network can extend up to 60 kilometers, which is also the logical reach. That is the reach for which protocols have been established. This is the same figure, but in the ITUT style, which means it's the reference diagram for the gigabit passive optical network. Pay attention that the direction is reversed. Now we have the central office here and the user on the left. In this diagram, there are some few points to be noted. The position of the interfaces of the optical distribution network, which are just after in downstream direction, the OLT, and just before, still in the downstream direction, before the ONU ONT. In the upstream are just after, just before. In the central office, we can have other network elements which can use, through a different wavelength, the same distribution network to provide different services. For example, this network element could be a video server, so that radio frequency video or digital video can reach the user. To this purpose, some WDM couplers, which are not really WDM multiplexer, they are working in both directions, are inserted into the network. If we pay attention to this WDM coupler, we see that the video will go this direction, the data will go this direction, the returning data will go this direction. So if we use two different wavelengths, we can have a properly working system. In this table, the main characteristics of the optical distribution network physical layer are listed. Yesterday you were asking about B+. Yesterday you were asking about B+. We can find here the attenuation classes which are defined in the relevant recommendation, which is G.928. And we can see that we have three different classes, which are A, B, and C, where A has a minimum attenuation of 5 dB, a maximum attenuation of 20 dB, and so on up to class C, which is 15 dB of minimum attenuation and 30 dB of maximum attenuation. After the first establishment of the recommendation, some modifications were introduced in G.982 to increase the reach of the system. So two new classes were introduced. The class B+, which is between these two, the range is extended, and the class C, which has a maximum reach which is more than 30, if I remember well, is 32. So you can find these new relevant classes, B+ and C+, in the last edition of the recommendation. This is the maximum differential optical path loss, which is 15 dBs, so that one of my slides yesterday was wrong because I put 20, please correct it. The right value is 15. And we have other parameters like the maximum logical reach that, as I already told at least twice, is the maximum distance for which protocols have been defined. And the bidirectional transmission, how can be obtained? Well, in all the examples I have been showing to you, for sake of simplicity, I have always put just one fiber which is used in both directions with some sort of WDM multiplexing, which means two wavelengths in the third window in the downstream direction, one wavelength in the second window in the upstream direction. Of course, you should have two directions, but you can get them also by using two different fibers. You are not obliged to use the same fibers with two different wavelengths, but you can use two different fibers. Of course, this is the recommendation, but the optical distribution network will be twice as costly from the point of view of the components as the optical distribution network, which has just one fiber, so that nobody for the time being is going to use the two fibers approach. Any question? Please. To double all the installation. If you are going to use two fiber, you will pay twice the fiber plant. Of course, the excavation costs, the laying cost will be the same, because if you put one fiber or you put two fibers, you will spend the same money. But the fiber is costly than having a WDM coupler here and here. Normally, the fiber has a much higher cost than the WDM couplers. The WDM couplers can be bought for a few tens of dollars. Well, let's go ahead. We are back to the one fiber or two fiber system with some terminology. According to recommendation G983.1, we can have the system operating in the so-called duplex working. Duplex working, which is different from duplex working, which is the next bullet, simply means that a single fiber plant is used in the two directions in the same time, so there is no time interval division, but in the same time we have the two flows going in the two directions, but they are going on the two directions on different wavelengths. Where the wavelength the same, we should speak about duplex working, but in optical distribution network we are always in a condition of duplex working. For duplex is not forbidden, of course, but all the installations that have been made up to now of gigabit passive optical networks are working in duplex mode. Different wavelengths in the two directions and the side towards the OLT or ONU, separating the two wavelengths in the two directions. This is a duplexer. It's exactly the same, but we have the same wavelength in the two directions. The last one is a triplexer, which is used to multiplex on the same fiber data, video, data in the other direction. It should be very clear how these devices can be used. Maybe you are the most expert in this field. In the triplexer, on the bottom line, where is the OLT? On the left or on the right? On the left, okay. Because the OLT is sending both 1.49 and 1.55 wavelengths to the network. This is a table which has been compiled just, this table is not appearing in the ITU recommendation, it's my own table, and it's reported only to understand how the splitting ratio can influence heavily the performance of the optical distribution network. On the first column, we have the splitting ratio, which can be 1-to-1. It means that there is no splitting at all. The fiber is going directly from the optical line terminal to the user. And starting from 1-to-2 up to 1-to-128, we have all the normally used splitting ratios. The splitting loss, the theoretical splitting loss, which means I am dividing the pulses between the users so that anytime I divide by 2, I introduce a loss of 3 dB, which means very clearly that if the splitter is 1-to-2, I introduce a loss of 3 dB. If 1-to-16 is 12, 1-to-16 is 2 to the power 4, so I have to take the exponent and to multiply it by 3. And this is the maximum loss in the splitter. This is the theoretical loss. We cannot have a loss which is less than this. But we have also to add the excess loss, which is due to the manufacturing process, which means that we are not able to develop a perfect component, a perfect device. When we fabricate it, we introduce an additional loss. This loss, in general, increases with the number of output. The excess loss provided are just an example. I decided that those were the excess loss. They are very close to the real values. And as you can see, they are increasing with the number of the output fiber. So the total loss can range from 0 for a direct connection to 24 for a splitting ratio of 1-to-128. It is also to be noted that if I adopt a two-level splitting, for example, instead of having just one splitter, 1-to-128 with a total loss of 24 dBs, I can use this splitter plus this one. If you add the two losses, they will be more than 24. This is an example of showing that having just one splitting level is better from the point of view of the characteristics of the network. Of course, gives you less flexibility. But normally, since we have excess losses, the sum of two excess losses of two different splitters, which are put into a cascade, are more than if I had just one splitter. Yes.
Thank you. When you say that displacing loss is, let's take an example. Yeah, splitting loss. Let's take an example of 1-to-16. I can see that it's 12 dB. This 12 dB, is it on, will be on each fiber, or is it a total?
On each branch.
On each branch. It means that from, let's say that you have one OLT connected to number 4, for example. It means that that 12 dB will be between the OLT and that ONT.
Any of the ONT.
Any.
If they are all at the same distance, because you have to add the fiber loss. I can, just a moment, I will draw a picture for him, and afterwards I will come back to you. So this is P minus 6 dB. This is linear power, this is in dBm. So the loss on this branch is 6 dB, but it's 6 dB also here, and here. From here I go to my ONU, and I have a fiber loss, which is 2 dB. I go to my ONU, which is very close, and the fiber loss is 0.5 dB. So the total loss on this path will be 6.5 dB. On this path will be 8 dB. Clear? Please.
Just see that the maximum split ratio was 1 to 64. Why do you consider case of 1 to 100?
Because 1 to 128 is considered a possible extension in the recommendation. It will be deployed in the future. It's possible to get that kind of? Yes. If you use, for example, rich extenders that we have a look later on, since you have the regeneration of the signal, the optical power just before the splitter will be high enough that you can add another 3 dBs of loss due to the high split ratio. But someone is already deploying 1 to 128 splitters. Yeah. There is no loss at all because you have a straight fiber. There is no splitting. Well, there is only the loss of the fiber, but this is only the loss of the splitter. Then you should add the loss of the fiber, 3 dBs. But this table takes into consideration of only the loss introduced by the splitter. Any other questions? Already have said it, and I will repeat, is evaluated taking into account the worst case approach. You should have learned what is a worst case approach and what is a statistical approach. I will repeat for the sake of clarity very briefly. Worst case approach means that during the design phase, you take into consideration for your design all the worst values that you can have for your particular parameter, which means that if I have a link and I take into consideration the attenuation of that link, the worst case attenuation will be, for example, 20 dB. It means that on average, the attenuation will be lower because 20 dB means that you are very unlucky. So maybe the average value will be 15 dBs with a given statistical distribution, which means that you can have a Gaussian distribution with a given variance and so on. In the worst case approach, you always consider the worst case attenuation value, 20 dBs. In the statistical approach, you use 15. You have a lot of concatenated pieces of fiber, and afterwards you will have a statistics on the attenuation, which means my total attenuation will be 30 dBs with this variance. It means that in a given percentage of the cases, which means in a given percentage of the optical path in the gigabit PON, you will have a link that will exceed the maximum values of the recommendation. To avoid this, for G-PON, only worst case power budget is allowed. You are not allowed to use any statistical approach. How the plant is realized? We start from the optical line terminal, fiber connector on a distribution frame, fusion splice, another fusion splice, another one. We have the splitter, connectors, fusion splice, another splitter. Sorry, this is not the splitter. The splitter is here. Fusion splice connector. So we put in the table of all the values of the various components. For example, fiber attenuation, the value is 0.4 dB per kilometer. We have 20 kilometers between the OLT and the ONU, so the total loss will be 8 dB. We have a 0.1 dB of attenuation per splice. We have 15 splice. The total loss will be 1.5 dB, and so on. We have connectors, 4 connectors. We have design margin, which means an extra attenuation that we add to the real attenuation to take into consideration future possible repairs or aging of the fiber. And we have one additional dB. This is the maintenance margin. At the end, we have the splitter, which has a theoretical attenuation of 15 dB plus 2.1 dB of insertion loss attenuation. So, as you can see, the total attenuation of this link is 30 dB. That means that this system can operate under class C. In a table that I showed you before, there were 3 different classes. The last one, class C, had the maximum attenuation of 30 dBs. This is a very important slide since it put into evidence what is the process to get the design of the network. Yes. 15 splices. You can check the value of attenuation of the splice. If it's lower than 0.1, you are lucky and you are happy. If it's more, you simply have to do it again. If the splice will be 0.4 or 0.5, you simply have to do it again because it's out of the design value. Because you have a margin here, a maintenance margin, but this is intended at the end of the life. So when building the plant, it's better to have the right values already. But I have some experience with the splicing machine because I was the controller of a big installation in Rome. They made at least 1,000 splices, and out of them only 10 were more than 0.1, and of course they did them again. So, yeah, 0.1 is a conservative value. It's not very difficult to reach. So I am surprised to listen. Yeah, maybe, but maybe it's an old value. The recommendation has not been changed anymore. Which recommendation is it? I will check. Yeah, but it may be. There are some inconsistencies, of course, because the recommendation have been prepared in 30 years. I'm not responsible for all the recommendation of ITO. Now we introduce a new concept, which is the concept of next generation access. Anytime we have a system working, we start thinking about a better system. So having a very good transmission network, having a very good access network, we start thinking about next generation networks. Concerning that, of course, we will have better performance, otherwise it would not be next generation. Concerning the access, people started thinking about next generation access. Next generation access is a new network with respect to passive optical network, but to save investment, it can be run on the same optical distribution network, on the same plant, on the same fiber plant. What does it mean? It simply means that suppose you have installed your passive optical network, and suppose you want to deliver new services which is not possible to distribute over the passive optical network with the protocols of that passive optical network. Well, the idea is to define a next generation access network, but which is still using the fiber plant you have. Because most of the investment in networks is under the ground. In the central offices, the equipment are costly, but after some years you can replace them with better equipment. To replace a fiber plant, it's a very costly operation. You have to excavate new trenches, you have to put the fibers again into the ground, and so on. So the idea is to preserve the plant. The second idea that immediately follows is, of course, to have the two networks working in the same time. So you have a gigabit passive optical network, which is working, which is delivering services. You want to install a new network, you will install on the same fiber plant, but without stopping the system. It simply means that since the bandwidth of your plant is practically not bounded, you will use a different wavelength. So, coexistence of next generation access and passive optical network simply means that you provide different bandwidth for different services on the same plant. This is the meaning of the recommendation 984.5, which is the last arrived, is a very new recommendation, which defines other wavelength ranges which are reserved for additional services running on the same passive plant. So, now we have three different sets of bandwidth. The bandwidth which is reserved for classical gigabit passive optical network, the bandwidth that will be used, or in some countries is used for next generation access, and the bandwidth that we have already introduced before for video services. The various bandwidth have some band intervals which are needed to minimize interference. Moreover, some wavelength blocking filters are used to block the interference from other bandwidth. These are words, but in a short while we will see the picture. This is the original picture from the recommendation, and you can see the upstream in the second window. The top line is the bandwidth which is allocated for G-PON, and on the middle row you have the enhancement band which is foreseen, which means between to be used in the bandwidth which is now usable by means of the new type of fibers. And for the third window, bandwidth, we have the original classic bandwidth, the basic band. I show you the wavelength of 1.49, which means 1.49 plus or minus 10. And these are the new bands that are foreseen to be used both with next generation access and video services. This is the same figure with some colors so that it's very simple to understand. I would have some other appearing. This is the bandwidth as defined in the G984.5. It's exactly the previous slides, less bureaucratic, let's say, with colors to fully understand what is the bandwidth allocation. As you can see on the top row, there is the subdivision of the total fiber bandwidth, which is between 1 26 and 168 in the various bands according to the definitions given in the recommendation. We have the O band, which is original band, enhanced band, short band, conventional band, large band, and ultra large band. Sorry, a long and ultra long band. And you can see which services are allocated or are to be allocated in the various bandwidth. The red is the G-PON upstream, the blue is the G-PON downstream, the yellow, pale yellow, is the radio frequency overlay, and the green is possibly, because as you can see, it is still dashed, so no final decision has been taken yet. And you can see next generation access passive optical networks, option 1 in band E, and option 2 in band C plus L. Of course, this is possible only with the new kind of fibers in which the water peak absorption has been reduced, which means fibers G.652.C or .A, or .D, sorry. This is finally the final picture of a gigabit PON. Please do not panic, it's very simple. If we start in an ordered way, from the left, top row, optical line terminal to drive signal for G-PON. Middle row, optical line terminal to drive signals for next generation access. Bottom row, optical line terminal to send video signals. Since they are in different bandwidth, on different wavelengths, they can be added or splitted by means of a WDM splitter. On the other hand, at the end of the optical distribution network, after the splitter has delivered all the signal broadcast to just one fiber, you can have a different ONU, and each one can be tailored to receive the wished service. So, top row, this ONU will be used only to receive G-PON. This one can be used to receive G-PON plus video, to receive only next generation access, to receive next generation access plus video. Why there is no example to receive G-PON plus next generation access? Because they will transmit essentially the same information. We are speaking about data transmission that can be transferred to the user either by G-PON, that at that time will be a legacy system, or via next generation access. The user will not decide to have twice the same information. So no ONU is foreseen to have access both to NGA and to G-PON. Seems to be clear. Everything seems to be clear. Okay.